Okay, we are live. Okay, hello everyone. My name is Christian Shakkour. I'm an MSc student at the Technion, and in today's presentation, I'll be presenting this paper called On Detecting Some Defective Items in Group Testing by Professor Nader Bshouty. Um, let's get started. So, the motivation behind group testing, which is called the classical group testing, is we have a group of n items, and there are d defective items in this group. Um, on this group testing, a test subset is a result of a test on the group where we are trying to detect defective items. So the test is positive if we find detective items and negative if not. Some of the applications of this group testing is blood testing, DNA screening, and COVID-19 pooled PCR testing. The goal of this paper on detecting some defective items in group testing is to try to challenge this and not detect all the D items, either detect L, which is a smaller subset of the defective items. Why would we want to do this? Because in a large groups where N is very big, and also the number of defective items is big, we might be able to get our results or get the answers by detecting less than D, which is a small L. Usually L is smaller or equal to D, the total number of defective items in the group. So the paper questions this idea and asks if we can do better in terms of algorithm time complexity. So why would we want to test L, which is less than the number of defective items? So some medical facilities don't have all the resources to test all the defective items. Let's give an example on the COVID-19, where we have a lot of people and a lot of defective items, which are people suffering from COVID. So we might not be able to test everyone on planet Earth, but maybe a small subset L. And this is the motivation behind this paper, to test less than the total defective items, which is L smaller than D. So to start talking more mathematically and algorithmically about this problem, we want to first declare a formal definition of the problem. So we have X is a set of all the items of size N, and we have I, which is a group that is intersected with X, is the unknown set of defective items. So I is all the defective items in the group X, and the size of I is equal to D. And we call a group test Q, which is inside of the group, which is part of the group X, is a subset of the test, and the result of the Q with respect to the defective set I is 1 if the group test Q has at least one defective item, else it is 0. So if Q has one item inside of the group I, which is the defective items, we return 1, else 0. So assumptions on D. Sometimes D, the number of defective items, is known. So when we say D is known, we have an estimate of D, which resides between D divided by 4 and 4D, which is the defective items. And when D is unknown, we have no information about D. So we have a group and we have some defective items. We don't know exactly how many defective items. That's the formal definition of the problem. Let's move forward. So for this problem, we have four testing models. One is adaptivity. So if the algorithm is adaptive or non-adaptive, the algorithm that does the group testing to detect L, D, or any number of defective items within the group. So adaptive says that each test can depend on the outcomes of all previous tests. So it's sequentially. So the first test goes, and then the second test can use the results of the previous test, and those tests are incremented sequentially. This is the adaptive method we call. We're going to see this a lot in the paper. And there is the non-adaptive, where every single test is independent of the rest of the tests, and we can do all the tests in a single parallel run. Usually, we're going to be using a fixed T by N matrices, where N is the number of items and T is the number of tests that we're going to be running on this group of items. Second of all, we have the second axis, which is randomizations. So some algorithms are going to be deterministic, where every single step is fixed and we know everything about the problem. And some of them are going to be randomized, like flipping a coin, where it could be that the next step of the algorithm is randomized, or the next input that we're going to put into the algorithm is randomized. So we have adaptability, adaptive, non-adaptive, randomized, and deterministic. And we're going to see all these combinations. We're going to see all the upper and lower bounds for all these combinations of algorithms. So again, we have adaptive, non-adaptive, deterministic, and randomized. So we can use adaptive with deterministic and randomized, and also non-adaptive with deterministic and randomized. So here we have the non-adaptive testings as a binary matrix. So I'm not gonna talk about what's written here. Let's directly look at the example. So we have the group has 4 elements, okay? And Q1 is the test that I'm be doing. So, and here we are given, we know the problem. We know that 2 and 5 are the defective items. Sorry, 2 and 5 are the defective items in this group. So Q number 1 is running a test on the first element and the second element only. Q number 2 runs a test on the third and fourth element only. Q number 3 on the second and fifth element, and Q4 runs a test on the fifth and sixth element. And the answer for these questions, so Q asks if 1 is defective, 2 is defective, and we know that 2 is defective, so the answer is 1 for this question, Q1. And for Q2, the answer is 0 because 2 and 5 does not reside within the checked elements. So we check element number 3 and 4, and they are not defective. So we have 0 defective items in the group Q2 question. And this is the binary matrix way of testing. We're going to be using this later. So from this slide forward, we have 3 main tools that we are going to be using along this paper to prove the upper and lower bounds of the time complexity of the algorithms that we're going to be using. So the first tool is the Chernoff bound. Chernoff bound basically is applied on a random variable that sits between the 0 and 1, that gives the answers 0 and 1, which is indicators, as we know from math. And this tool basically says that if you flip a coin 100 times, probably you're going to get 50 times head and 50 times tail, somewhere in between. So this Chernoff bound gives us an upper and lower bound for this result. So it is it's very unlikely to get 90 heads when flipping the coin 100 times. So this Chernoff bound gives us an upper and lower bound, if we can see where X is the group of indicators. And if we take big notation X to be the sum of all the indicators, and mu is the expectance of these indicators, the probability of X, which is the sum of indicators, to be greater than some value that is multiplied with the expectance diminishes very rapidly as we try to go beyond the expectance. So if we're asking ourselves what is the probability to have 90 heads instead of 50 in 100 coin flips, well, this probability is very low and diminishing. So this gives us an upper bound, which is related to the expectance of the random variable that we're working with, upper tail, and also a lower tail, which is, if you can think about it, it's basically a Gaussian function around the mean of the function. So if we go way higher than the expected value, the probability of us landing there is very low. And also, if we go very low beneath the mean value, which is the expectance, the probability also is very low. So we are going to be using this tool later on in this paper to prove upper and lower bounds of the results that we're going to get from the algorithm. And that's about it. Let's move to the next tool, which is Yau's min-max principle. So the purpose of Yau's min-max principle is to prove lower bounds for randomized algorithms. This one is a very important tool we're going to be using a few times. The principle says, let's talk about this, the expected cost of the best randomized algorithm on the worst case input. I'm going to go over this again, the best randomized algorithm. So if we have a randomized algorithm and an input that goes into the randomized algorithm. So if we take the best randomized algorithm, the best one, the best performing algorithm, and input to this algorithm the worst input possible, we get that this is the cost of this is greater than the cost of using a best deterministic algorithm. So here we're trying to find a relation between randomized algorithm and deterministic algorithm. So if you take the best randomized algorithm on the worst input data, the cost of this algorithm should be greater than the expected cost of the best deterministic algorithm on the worst case distribution over inputs. So here we're moving where the algorithm is randomized, but the data is fixed, and finding a lower bound on where the algorithm is fixed, but the data is distributed very badly. So here we go. Let's take a notation of this math equation over here, or math inequality. So we are trying to take the expectance over the cost of AS. AS is the algorithm, is the randomized algorithm with seed S. So every time we roll out a different seed, we get a different best performing randomized algorithm, and the input is fixed. So we have a fixed input, a random algorithm, the cost of it. So the expectance over the seed of the cost of a random algorithm with a fixed input. If we take max on this, we get the cost, the highest cost of the worst input on the best performing random algorithm. And from the Yau's min-max principle, it says that it should be greater than the minimum over A. A is a fixed deterministic, let's not say fixed, deterministic algorithm over I. And the I here is the random variable where the input is distributed. So we take the minimum performance, minimum cost over a deterministic algorithm A with respect to the expectance over I, which is the worst case distribution over the inputs. Okay. So we're going to use this to prove lower bounds where we can take a randomized problem and lower bound it with a deterministic problem to find the lower bound of the randomized problem. So if we have a randomized problem, we move it, we find the lower bound of it on the deterministic problem. That's Yau's min-max principle. The third tool is Markov inequality. So the statement says for a non-negative random variable x with an expectance of x equals mu, the probability of x to lie greater than a, any number, is smaller than the mean of it divided by a. So the intuition here is a non-negative random variable cannot be large too often, otherwise its mean would be larger. So this is also used in lower bounding proof for non-adaptive randomized, where D is unknown. We're going to be seeing these later. This is the Markov inequality. And now we're gonna start looking at the results. So first of all, I'm gonna display the detecting D defective items out of N defective items, which is a known information. Our paper deals with the L defective items out of D. But this we will look at this just to understand how to read this graph, and we're gonna also compare the results of this paper to this data. So that's in general. We don't need to look at it a lot. So let's move into our results from the paper. So detecting L defective items out of D defective items. This is the table that we're going to be focusing on, and also proving each and every one of those bounds. They are enumerated with numbers 1, 2, 3, so it could be easier to in the future in the next slides to exactly know what we are trying to prove. So let's firstly understand how to read this graph. We have, first of all, the adaptive, which is those 8 pairs, and the non-adaptive. As we said, the adaptive is where the algorithm runs sequentially, and there might be dependencies between the results in between iterations, and the non-adaptive where all the algorithm can run in parallel at the same cycle or at the same iteration. So for the adaptive, we also split the algorithms into randomized and deterministic. So if we look at the bound here, number 1, it's an adaptive algorithm, it's deterministic, and D is known. D, the number of defective items in the group, is known. So the upper bound for an adaptive deterministic D is known algorithm is L log N divided by D. That's an example. And if we try to read 7, it's an adaptive randomized D is unknown algorithm. So 7 is the upper bound of an adaptive randomized D is unknown algorithm. Okay, so we're gonna split the presentation into 2 parts. The first part we're gonna talk only about the adaptive algorithms, and the second part we're gonna display and explain or prove all of these terms in the non-adaptive term. So let's first of all start with the adaptive results. Here I have them just put together, not in a table, separated from the non-adaptive results. We are at the end, we're gonna see those key observations again. And let's move on. So 1, 2, 5, 6, 3, 4, 7, 8. These are the lower bounds we saw in the previous slide. We're gonna prove them each. Let's start by 1 and 2. So this is the first part we're going to start with 1, 2, 3, 4. Let's prove these adaptive deterministic algorithms where D is known and D is not known. We have 4 algorithms here, or 4 proofs to take. Let's get started. So theorem number 1, which corresponds to results 1 and 3. Let's take a look again at the results 1 and 3. So we have an upper bound for an adaptive deterministic algorithm where D is known or not known. Turns out in the proof that it doesn't matter if D is known or not known in this case. We have the same upper bound, which is L log N divided by L. N is the total items in a group. L is the defective items we want to take a look at. And in contrast to the D defective items where there are algorithms that try to find D out of L, we have N divided by L times L, and not N divided by D times D, which is smaller. Let's prove 1 and 3. So the theorem says that there is a polynomial time adaptive deterministic algorithm that detects L defective items and makes at most L times log N divided by L plus L 3L tests. This works whether D is known or not. So the proof goes like this. If we take the whole group X size N items in total and divide these groups into L disjoint groups. Again, L is the number of defective items we are trying to find. So if we divide it into L disjoint groups, we call them X1 till XL, Xi, of size N divided by L each. So for each group we have divided, if we run a binary search to find the defective item, it's enough to check if one exists. And for every group, after we find one, we stop once L defective items are found, okay? So we take X, we divide it into L groups, and for each group, we run a binary search algorithm. So let's take a look of why it works, why the upper bound is L log n divided by L. Since D is greater than L, by the pigeonhole principle, at least one of the L groups contains a defective item, okay? And also, when we run a binary search on each group, we know that the time complexity of a binary search is log n divided by L. So it's log the size of the group, and we know that we have divided each xi into a group of n divided by L size. So from here, we get the log n divided by L plus 1 test. So for each group, we run log n divided by L plus 1 tests. And we have L groups like this. So this is why the upper bound for the adaptive deterministic algorithms comes from. So the cost analysis is testing all groups. It is L tests. Binary search within each group takes L log n plus L plus 1. So if we multiply this by L, we get the total of L log n divided by L plus 3L. So it is equal to the time complexity of O of L times log n divided by L. So this is the proof why theorem 1, results 1 and 3 have an upper bound of L log n divided by L. It's because of this type of algorithm where we divide each group into n divided by, we divide the whole group into L disjoint groups and run a search on each group to find at least one defective item. So theorem number 2 comes to prove the second result. It says any deterministic algorithm A that detects L defective items must make at least a maximum between L log n divided by D and log n minus 1. So let's go over it. Any adaptive deterministic algorithm. So we take an adaptive deterministic algorithm, we call it A, any algorithm that detects L defective items must make at least maximum between L log n divided by D and log n plus 1. Okay, so the proof is comes from the counting argument. We let L1 till LT be all the possible L subsets of the algorithm A can output. So if we take the algorithm A and run it on X, which is the group of all inputs, so each time we run the algorithm A, we get a different subset of L defective items. So we run the group, we run A on the group X, we get a subset Li that has L defective items. And we run this again and again and again, we get different L1 subsets of the algorithm. And for each L1 is a size of L. So we get, let's generalize this. We run the algorithm, we take all the unique subsets that this algorithm yields. We call this T. This is the number of unique subsets, L subsets that the algorithm A can output. So since the algorithm A is deterministic, its test complexity is greater than log of T. Okay, so T is the number of subsets. There must be the time complexity, the test complexity must be greater than log of the number of subsets we have. Okay, so it's log T. For each Li, the set of D defective items, each Li can be output at the most n minus L, choose D minus L inputs. So from Li is a subset of the defective items. So there are n minus L, choose D minus L unique subsets like these. And since there are n choose D possible defective sets, so we can say that T is greater than the size of these all subsets, all unique subsets, is basically the division between the total number of subsets given D, total number of D choose N, N choose D items, divided by all the possible options, which is N minus L, choose D minus L. And if we open the calculation and put this in the equation, we get that t is greater than this t is greater than n divided by d times L. Okay, with the power to the powers of L. Therefore, if we take log on both of the sides, we get that log t is greater than, since log is a positive function, it maintains the inequality sign. So if we take log t and log on the other side, we get that log t is greater than L times log n divided by d. Okay, so this gives us the first bound for the function. We split it into groups. We split it into L subsets, and we know that there are T L subsets, T unique L subsets. This T should be greater than this equation, which is D choose N choose D divided by N minus L choose D minus L, and we take log on both sides to get the lower bound. And for the additive log n minus 2, for log n bound, if t is smaller than n minus d, one can construct a defective set I of size d that avoids all output. So t greater than n minus d and log t output. So we get that t is greater than n minus d. And if we take log on both sides, we get that log t is greater than or equal to log n divided by 2, which is equals to log n minus 1. This is why we get the n, and the test complexity is the maximum between those two operands. So theorem 3 says any adaptive deterministic algorithm that detects L defective items must make at least L times log n divided by L tests when D is unknown. So we have this algorithm. So to prove theorem number 3 or result number 4, we are going to be using theorem number 1, okay? So the only thing here is that D is unknown, in contrast with theorem 1, where the number of defective items in the whole group is known. So what we are going to be doing here is to we know that the algorithm in theorem number 1 works for any size of D. So we choose D to be 4 times L, and we put the upper bound on this result. In this theorem, D is unknown, but we are using D to be 4 times L, and then for the algorithm, it becomes known. So by theorem number 2, we get, sorry, theorem number 2, not theorem number 1, we get that L log n divided by D, and then we plug D to be 4L, and we get L times log n divided by 4L, which is equal to L log n divided by L minus O of L. This is the test complexity. The lower bound of result number 4, text complexity, which is the adaptive deterministic algorithm. The lower bound of the adaptive deterministic algorithm using theorem number 1. So we have first explained these lower and upper bounds, the deterministic and adaptive deterministic lower and upper bounds for these algorithms. So if we take a look, we can see that 1 and 3 have the same upper bound. So it doesn't really matter if D is known or unknown. The adaptive deterministic algorithm has the same upper bound. 4 also has the same upper bound between 3. So upper and lower bound are the same bounds when the adaptive deterministic algorithm where D is unknown. And these are the observations on the adaptive deterministic algorithms. Now we are going to take the adaptive randomized algorithms. So it's 5, 6, 7, and 8. Let's go ahead. One thing to keep in mind, on these, the log, inside the log, there's n divided by L, and here there's n divided by D. So it's a little bit worse when we have a randomized algorithm where the algorithm has either the inputs distributed in some way, or the algorithm itself, the steps that the algorithm take are with a certain probability. Okay, so let's go over 5, 6, 7, and 8 and prove these points. So theorem number 4 is related to result number 5. We have an adaptive randomized upper bound where D is known algorithm. So randomized again is where the algorithm could give us an output in a randomized with a probability. So the algorithm performs or gives us the output L with a certain probability. So this theorem has two proofs. We are going to first look at part number 1, the first part of the proof. Let's first of all take a look at the theorem and then dig deeper into the proof of why this works and why we have chosen this upper bound. So we say let L be smaller than D divided by 2. L is the number of defective items we're looking for, and D is the total number of defective items. And D is an integer that resides between D divided by 4 and 4D when there's a randomized adaptive algorithm that makes. So given these two constraints, there is a randomized adaptive algorithm that makes L times log n divided by D plus L times log of 1 divided by delta plus O of L tests. And with probability greater than 1 minus delta detects L defectives. So this algorithm detects L defectives with probability greater than 1 minus delta. So it doesn't always give us the right L defectives. It gives us the defectives with a certain probability, okay? So first of all, we're going to take the case where D is smaller than C times L, where C is defined as 32 times log 2 divided by delta. Delta is any rational number. So here we can say that if D is smaller than C times L, we can use the deterministic algorithm in theorem 1 because there is no probability in this case. If D is smaller than C times 1, there is no probabilistic results. We are always going to get L defective items. And to prove the upper bound, in this case, where D is smaller than C times L, we just plug in the test, plug in into the test complexity of theorem 1. So if we take theorem 1, in theorem 1 we had this test complexity L times log n divided by L plus 2L. And now we are going to plug L to be D divided by C from here. And we get that it is equal to L times log n divided by D divided by C plus 2L. And this is equal to L times log n divided by D plus L log of 1 divided by delta plus O of L. So this is the upper bound of theorem number 4, which is result 5 for the adaptive randomized upper bound. And D is known. We know the number of defective items. The first part of it, where D is smaller than C times L. And so this is the first part. The second part, we're going to see the opposite case, where D is greater than C times L. So we have the same setting of the theorem regarding result number 5. Part 2, where D is greater than C times L. So we have the same C defined here, 32 times log 2 divided by delta. Each element x, and then we do something to choose the x's. This is the probabilistic part of the algorithm, the randomized. So each element x inside of big X, which is the group of all inputs, is included in X prime independently with probability of CL divided by D smaller than 1. So we create another group called X prime, and this X prime has the elements of X, each element independently with probability of CL divided by D smaller than 1. So the new group X prime is not precisely the group X. It is the group X and for each element individually with a probability. So we say like this: if the size of the new group X prime is smaller than 3 times C times L times N divided by D, we can deterministically detect L defective items in X prime using theorem 1. Why this actually works? Because in general, if we say that X prime is a new group that has the size of X prime but has at least L defective items, we can run any deterministic algorithm over the new group X prime to get the upper bound of this. So this is what we're gonna do basically on this theorem. And we have the new group X prime. If this holds, it is guaranteed that this X prime has at least L defective items or greater than L defective items, and hence we can use a deterministic theorem. So let's look into the math of why this works. And we're going to be using here the Chernoff bounds. So let's say it like this, number of defectives in X prime. So X prime, we have to define a new group, a new number, which is y is the sum of all the indicators, yi, which they are spread Bernoulli. Each yi is basically an indicator that returns 1 if the ith defective item is present in X prime, okay? So y1 is if the first defective item is appearing in X in the group X prime. So this is why we have the size D, because we have D defective items, they are known. So we have indicator for each D index, which is y runs from y till D, and y big Y is actually the sum of all the indicators. So we can say that the expectance or the mean of this sum of indicators is equal to C times D times L divided by D, which is greater than CL divided by 4. So by Chernoff, we can conclude that the probability of Y to be smaller than L, this is what I was trying to explain here, that the probability of having less defective items than L in the group X prime is smaller than delta divided by 2. Okay, this is what this line is trying to prove, that the probability of the sum of indicators of defective items in the group X prime is smaller or equal to delta divided by 2. In the next slide, I will be explaining exactly how they got into this result, but let's take it as is for now and continue the proof. So we also know a thing about the size of X. To use a deterministic algorithm, like in theorem number 1, we need, first of all, to make sure that there are L defective items, at least L defective items. And this is what we proved here. And we also need to make sure that the size of X is, first of all, greater than L and also smaller than N. So we have here another thing to see about the size of the group X prime. So the expectance of the size of the group X prime equals to C times L times N divided by D, which is a number. And by Chernoff, we can prove that the probability of the size of X to be greater than 3 times CLN divided by D, which is 3 times the mean, is smaller than delta divided by 2. which is exactly the assumption we're putting here to prove the algorithm. So we assume this, and then we prove it using the Chernoff. And with this proof, we also can use the assumption, the information regarding the number of defective items we found in X prime to run a L defective algorithm using to use an adaptive deterministic upper bound that we proven in theorem number 1. So if we plug that in, the test complexity of theorem number 1, giving that we have a new group X prime and we have the same L defective items. So without this proof, we can't use this equation from theorem number 1. Okay, so the test complexity is L times log the size of the group X prime divided by L, the number of defective items. And this is inferred from theorem number 1, where we prove the upper bound of an adaptive deterministic algorithm. So now let's show the proofs for these two lines. So first of all, this one, we wanted to prove that the probability of the sum of indicators, which is the size of xi, is less than L. So there's less than L items in the group X prime is smaller than delta divided by 2. So this is the Chernoff rule. I just copied it here so it could be in front of us to see it. If we choose, and now we want to substitute L, you find the right representation of lambda and mu to be exactly L. So if we choose mu to be CL divided by 4 and lambda to be 1 minus 4 divided by C, and we plug them, we get L. So these are possible candidates to replace L. And then if we plug Chernoff, we start from the upper inequality. So the probability of Y to be smaller than L, we plug these in the Chernoff equation. We get e to the minus 1 minus 4 divided by C squared times CL divided by 8. And now, to move on to the higher bound, to the right side, we know that lambda resides between 0 and 1. So if we plug 1 instead of lambda, we actually find a higher bound. So we put 1 over here and get rid of this part of the equation. So we get e to the minus CL divided by 8. And now if we make the 8 larger, we get a even bigger bound. And it's the e to the minus CL divided by 32. And now if we plug C here that we saw earlier, we get exactly this bound, the delta divided by 2. So we have proven that the probability of Y is the sum of indicators of the number of defective items inside the group X prime is smaller than delta divided by 2. We can do the same for the Chernoff bound and we get the same result. This proves the previous part where the test complexity for adaptive randomized D known algorithm, the upper bound of it is exactly L times log the size of X prime, which could be bounded with a higher bound of L times log N divided by D. So now we move on to theorem number 5, adaptive randomized lower bound, where D is known. So theorem number 5, results 6 and 8, uses the Yau's principle, the principle where we explained, where we try to take a randomized algorithm and find the lower bound using a deterministic algorithm. So we let D be greater than L and smaller than N divided by 2, which is the half of the group, and D is known. Hence, any adaptive randomized algorithm that with probability greater than 2/3 detects L defective items must make at least L times log N divided by D minus 1 test. So let's prove this via Yau's principle. Let A SI be a randomized algorithm. So A is a randomized algorithm, S is the seed of randomization of this algorithm, and I is the input to this algorithm, which is the group X, all the items in the group. And we say that XSI be the indicator random variable that returns 1 if the algorithm ASI returns a subset L of size L. So why are we doing this? Because the algorithm that is used above detects L defective items with probability of greater than 2/3. So it doesn't always detect L defective items. So we turn the algorithm A and we create an indicator X, which is also dependent on the seed because it uses the A algorithm to return 1 if the algorithm returned a positive subset of L of size L. If it didn't return a positive subset, so the indicator is 0. So for every input we plug into this indicator, the expectance with respect to S, the seed of the algorithm of the indicator SI is smaller than 2/3. We know that the algorithm returns L defective items greater than, in a probability greater than 2/3. So the expectance with respect to the seed of XSI is smaller than 2/3 as well, the indicator. So now we know we're going to use the swap method. So we're going to swap the expectations. So the expectation of with respect to S of the expectation with respect to I of the indicator SI is equals to the expectance of respect to I, the input group, with respect to over the expectance of S, the seed of XSI is greater than 2/3, where EI is over the uniform distribution on all D subsets of N. So now that we know this information, we can say that there exists a seed S0 such that the expectance of over the input I of XSI 0 is greater than 2/3. So the deterministic algorithm ASI succeeds on at least 2/3 of the overall input group. Okay, so if we have N choose D, it's all the input possibilities, all the defective input possibility groups. And we know that the deterministic algorithm with respect to this seed that we have seen before succeed on at least 2/3 of the inputs. So using Yao, we have transformed this problem, Yao's principle, we have transformed this randomized problem into a deterministic problem where the randomization is not on the algorithm. We have made the seed static. We have an algorithm A with a static seed over an input that is non-deterministic, which is distributed. And we know that it succeeds on 2/3 of the overall possible inputs, which is the N choose D defective items. So from this information, we can use theorem number 2, which we proved earlier with where we have split the group into subsets, L subsets. And from there, we can plug this information where where A succeeds on at least 2/3 of the group. So if you plug it here, we get 2 divided by 3 times N choose D divided by N minus L choose D minus L, which is greater than L log N divided by D minus 1. So we have taken here an adaptive randomized algorithm. We found a seed. We proved that there exists a seed where for this adaptive algorithm, for this deterministic algorithm giving this seed, we succeed on 2/3 of the inputs to return the required information, which is to detect L defective items. And from here, we used this to plug into theorem number 2, which is the deterministic algorithm that yields this lower bound. We can lower bound it by this bound. This proves theorem number 5, results 6 and 8. Results 6 and 8, because D is known or unknown, it doesn't really matter if D is known or unknown. if D is known, this is the proof. If D is unknown, we can give a certain D that we know that resides in between those numbers and use the same proof. So if D is known, we use this proof. If D is unknown, we predict D within the right range and use this algorithm um, to prove the same lower bound. So when D is known or D is unknown, this we get the same lower bound for the adaptive randomized algorithm. So theorem number 7, adaptive randomized where D is unknown. So this algorithm says that there is a randomized adaptive algorithm that detects L defectives and makes L times log n divided by D plus O of L plus log of minimum of n divided by D. So the idea here is step 1, we estimate D within a constant factor, okay? We don't know D, so we estimate it within a constant factor. And then use lemma 3, an adaptive algorithm that makes O of log minimum D of n divided by D tests and outputs D with 1 minus epsilon times D, where D resides between those two bounds, 1 minus epsilon D and 1 plus epsilon D. So using this lemma, we can use theorem number 4 with the same estimate D, since D is approximately equal to D because epsilon is usually very small, and we know that we have bounded big number D in between plus or minus D. So we can use theorem number 4 to prove theorem number 7. Theorem number 4 is the adaptive randomized upper bound of D is unknown algorithm, and plug it directly into the upper bound and get the L times log n divided by D plus O of L. So how this estimation works and why? Test random subsets of geonomically increasing sizes. When test starts being positive, the size gives an estimation of D. And doubly exponential growth, only O of log of n divided by D rounds needed. So the lower bounds follows from theorem 5, same for D is unknown. Okay, so now we are going to move on to the non-adaptive results, the deterministic and randomized non-adaptive algorithms, which is these results from the table, which is results 9, 10, 11, 12, 13, 14, 15, and 16. These are the results, which is this table. So first of all, we're going to start with the non-adaptive deterministic and move on to the randomized. So let's go over these proofs, 9, 10, 11, and 12. And for this, we have to, first of all, start with this definition. So an RS restricted weight 1 matrix. Let's explain what this is. So A, RS restricted weight 1 matrix T by N matrix M is a binary matrix such that any R columns in M contain at least S distinct weight 1 vector. So a weight 1 vector among R columns is a row where exactly one of the R columns has a 1 in it and all the others are 0. So if we have a row, all of it is 0 except only one element is 1. And the intuition is that among any R columns, at least S of them are uniquely identifiable. Each has a test where it's the only one of the R that participates. Unique test, we can call this. Only one test is present in this row. If that column is defective and the test is positive, we know it is defective. Okay, so the index, the 1 inside of this row is defective. And the connection to the group testing is that we're going to see in the next slide in the algorithm that most of if we define a matrix that is 2D and D by L restricted weight 1 matrix, we can ease up the work and use a few lemmas that will lead us to a result. The bounds that we are looking for. Let's see a more visual explanation about this. So if we take a matrix M and we want to see if this matrix corresponds to RS restricted weight 1 matrix. So if we try to search for R equals 3 and S equals 2, we can see that for any three columns we take, so we're taking here C1, C2, C3, and we're going to generate a submatrix out of it, which is M prime. So this matrix that we have taken from the original matrix, we need to check how many rows of distinct weight there are. So again, the row has to have only um, one active in the only one column which is active. So here we have 1, 2, 3 of those. The fourth one is not. So we have 3 of those, and an RS restricted weight 1 matrix says that there has to be more than S, greater or equal to S, which is 2 in this case. So we have found 3 out of 2. So this one is a 3 by 2 restricted weight 1 matrix. If we take a look at this, we can also say that it's also 3 by 3 weight restricted matrix. So if we take any two columns, we can get a three unique rows where only one weight is active, only one test is active. This image is generated by AI. Gemini used Gemini to generate this picture for more visual. Okay, let's move on. So we're going to start now with a few lemmas before we prove those upper and lower bounds. So lemma number 6 says that let M, a matrix, be a 2D by D plus L, which is the RS, restricted weight 1 T by N matrix, and let QI, the question, be the number of column which in the index of the matrix ij, there is 1. So as we seen earlier, it's the index of the column which equals to 1. This is the question I. So the question in the row I of the matrix, of the strict weighted matrix, is equals to the question in the column, column J, the number of column J, which corresponds to Mij equals 1 for I in the T, which is the number of rows of the test matrix. So property 1 of this restricted weight 1 matrices is that for every two sets A included and B included in the set from 1 to n, where the size of A is equals to D and the size of B equals to 2D. So the property says that there is a test Qi such that the intersection of Q with A, the group A, is equal to an empty group, and the intersection between Qi, the question, and the group, the set B, is equal to an empty group. Okay? It does not equal an empty group. So if we want to put this in words, there exists a test that misses all of A but hits something in B, B excluding A, which is the elements that are present in B but not in A. So in easier terms, the matrix can always tell A apart from B. This is the property number 1. And property number 2 says that for every C which is included or equal to E, which is included or equal to the set from 1 to n, where the size of C equals D and the size of E is smaller than 2D, there are L tests, QI1 to QIL, such that each hits exactly one element of C. And these elements are all distinct. So in words, L defective items can be individually certified by separate tests. So to detect L defective items, we can say that we can find a unique test for each to detect one element. So they can be individually certified by separate tests. So for each L, I can to find each defective item, I can separate it into a single test. These properties are what makes the non-adaptive algorithms work. We're going to see this in a few slides. This is lemma number 6. So lemma number 7 states that if we let S be smaller or equal to C times R for some constant C in between a half and 1, and let T the number of rows in the matrix, okay, it's a matrix of T by N, which is O of R log N divided by R plus log 1 divided by delta, all of this divided by log 1 divided by C. So if we consider a T by N 0, 1 matrix where M matrix M where each entry Mij equals to 1 independently with probability 1 divided by R. So if we take a matrix and each element in this big matrix of size T by N is probabilistic. So there is 1 in probability of 1 divided by R and 0 with probability 1 minus this probability. Then with probability of at least 1 minus delta, M is a RS restricted weight 1 T by N matrix. So if we take any M matrix with the indices 0 or 1 in each of the elements with probability, there is at least with a probability of 1 minus delta, a matrix M prime, which is a RS restricted weight 1 matrix of T by N. Okay. I want to put another note here that Mij is, if you remember the first few slides, is actually the questions I'm going to ask about these sets. So if we have the number of rows, number of columns is all of the items n that we are trying to search the defectives in between, and the t is the number of rows, which is the number of tests I'm gonna be running, and each one in each row, which is the test, the ones are the questions I'm asking about these elements. So if we take a random matrix with probability of 1 divided by R to have a test in the column R on this element, we can say that with a probability of at least 1 minus delta, there it is an RS restricted weight 1 T by N matrix, okay? So in particular, if we take delta constant, there exists a RS restricted weight 1 matrix with T equals O R log N divided by R divided by log 1 divided by C. So if we read this statement aloud, a purely random matrix, each entry an independent coin flip with bias of 1 divided by R, which is I exactly explained. The density 1 divided by R is exactly tuned, so each block of R columns sees many weight 1 rows, okay? So there is a lot of elements that I'm going to be questioning with this density. This lemma is used in theorem number 8 with these parameters. We're going to see this later. So lemma number 9 states that given a 2D and D plus R equals 2D and S equals D plus L restricted weight 1 matrix M, the algorithm is that we run all T tests, answer I equals the test on the Qi, okay? And we let X prime be the group of elements from 1 to n, and Y an empty group for now, or empty set. And for I equals 1 to T, all the elements in T, all the tests in T that I'm going to be running, if the answer of the test equals to 0, then we exclude this question from X prime. We exclude the element of this question from X prime. And for I equals 1 to T, we do this again. If the answer of I equals 1 and Qi, the question, intersects with the group X prime equals 1, then we push this element into the group Y. And then this algorithm, after this runs on all the matrix, we exit the output Y. Why it works? So step 3 removes items from the negative tests. Okay, so each test that is negative, that did not detect a defective item, is excluded from the X prime. And then we can say that the size of X prime, so X prime has all the defective survival items, and the size of X prime is known to be smaller than 2D. So if we look at property 1 of lemma 6, if the size of X prime is greater than 2D, there would be a negative test hitting X prime, hence there is a contradiction. Okay? So there can't be, there can't happen that the size of X prime, which is all the positive defective items, that is greater than or equal to 2D. So it must be smaller than 2D. And step 4 identifies the detectives that are alone in their test within X prime. So we identify tests that are unique. And by property 2 of lemma 6, at least L such defective items exist. Okay, so therefore the output Y contains at least L confirmed defective items. So we know if we run this algorithm on a 2D, on R equals 2D, S equals D plus L, and restricted weight 1 matrix M, we are guaranteed that by the end of this algorithm, we have a set Y that contains at least L confirmed defective items, okay? So theorem number one, which is the first result, we are gonna test the non-adaptive deterministic upper bound where D is known. We know the size or the number of defective items. And our theorem says that there is a non-adaptive deterministic algorithm that detects L defective items and makes a test complexity of O D times log n divided by D tests when big notation D is in between D divided by 4 and 4D, which is known. And the proof goes like this, like this. If we take lemma 7, which we have seen before, a 2D and a R equals 2D and S equals D plus L restricted weight 1 matrix T by N, that exists with T, the number of rows, which is equal to O of D times log N divided by D. And this is constructed from a random binary matrix where Mij equals 1 with probability 1 divided by 2D. So as we saw before with lemma 7, if we take a randomly constructed matrix, T by N matrix, which is its elements, each element is either 0 or 1 with a probability, 1 with probability of 1 divided by 2D and 0 with the reverse probability, which is 1 minus this probability. So if we take a big matrix and construct from it a restricted weight T matrix exists, so we know that the number of rows corresponds to this complexity, which is D log N divided by D. And by probabilistic argument, which is lemma 7 and Chernoff bound, this matrix satisfies the property of high probability. So we can use lemma number 8. And lemma 8 says that this matrix yields a valid non-adaptive algorithm. So we brought in a matrix, which is Mij, and constructed from it with probability a restricted weight 1T matrix, and used lemma number 8 to get a group Y, which has at least L defective items. And from this, we can use any valid non-adaptive algorithm to test, which yields a D times log N divided by D, and it is not dependent on L. So even if we have a big group N and we want to test L defective items, which is any number, even if it's 1, the smallest, we still have to go through this test complexity, which is D log N divided by D. And it's also identical to the upper bound when we are detecting D defective items out of N and not L, which is previous work. And theorem number 9, which is result number 10, we are gonna now test the lower bound for the previous test. So we're running over the non-adaptive deterministic lower bound where D is known. So it says that any non-adaptive deterministic algorithm that detects one defective item must make at least a gamma of D times log N divided by D tests. Okay, so the proof goes like this. If we let M be the T by N test matrix, let Mj denote column J. So step number 1, for any defective set I, removing one defective must change the answer vector. Okay, if we remove one defective from the algorithm we're running on this set, it's gonna change the answer. Therefore, every W column, so if we take W that's equals to D to 2D, there must contain a weight 1 vector. So if we take this big matrix and we take the columns that we take a number of columns which is between D and 2D. Within these columns, there must be a weight 1 vector, okay? A weight 1 vector matrix. So now in step 2, this implies every 2D columns are linearly independent over GF2. So if it's not XORed of some D subset of columns equals 0, contradicting step number 1, okay? And step number 3 says that the XOR of any D columns is distinct from the XOR of any other D column. So if we take the first 5 columns and any other 5 columns, the XOR between them is distinct. So they are not 0. The XOR is 1. There is a difference between these tests. And it says that if 2D sets had the same XOR, their symmetric difference would be smaller than 2D columns would XOR to 0. Okay. And step number 4 says that therefore there are at least choose n distinct binary vectors of length t, and then we can say that 2 to the powers of t is greater or equal to n choose d, which if we move this to a log, if we take log on both sides, we can say that the log of t is greater than log of n choose d, which corresponds to the d log n divided by d complexity. And this connects to the parity check matrix bond in coding theory for any of you who know. And that's the theorem 9. This is how we prove the lower bound. So theorem 10 says the non-adaptive deterministic where D is unknown. So we have, in this case, we have results 11 and 12 where D is known or unknown, it's the same. We get the same result. If D is unknown, any non-adaptive deterministic algorithm that detects one defective item must make at least theta of n tests. So the proof goes like this. Suppose for I0 is the set of elements from 1 to n, the algorithm outputs I1 for big I1 equals to all the set from 1 to n, excluding I1. It outputs I2, okay? So I2 is equals to the exclusion of all the set from I1. Since output for I0 differs from the output from I1, there must be a row in M that is 1 in entry I and 0 elsewhere else. So it's some sort of a unique weighted row, okay? The rows we have seen where there's only one element, which is 1. And now, since the output for I1 differs from the output of I2, there must be a row in M that is 1 in entry I2 and 0 in entries n, the set of 1 till n, excluding I1 and I2. And if we count M, if we start counting these entries, we get that M must have at least n rows, 1 per item, okay? So there must be n rows, and there must be 1 test per item, okay? So the upper bound trivially tests each item individually. So there's n tests. We need to run n tests to test this to detect L defective items. And the conclusion is that knowing D or knowing D in the non-deterministic testing gains nothing over individual testing. Okay, so if we individually test each and every element to detect L defective items, and if we use this algorithm, which is the non-adaptive deterministic, we don't get any gain. So we must have n tests in order to detect L defective items where whether D is known or D is unknown. And that's the theorem 10 results, 10, 11. Okay, so now we move on to detecting L defective items out of D defective items for the non-adaptive randomized settings or algorithms. Let's take a look at this. So in the randomized, we get the L log n divided by D, upper and lower bound, it doesn't matter. Where D is known and where D is unknown, we have a L log squared of n and a log squared of n divided by a factor of L and n, okay? So now we're going to prove these results, 13, 14, 15, and 16. Let's go ahead. So first of all, I'm going to start with a lemma number 9. There is a non-adaptive deterministic algorithm that makes t equals log n plus half log of n plus O of 1 tests and decides whether d is smaller than 1. And if d is equal to 1, it detects that defective item. So t is the number of tests, again, in the matrix we are working with, or the number of rows in the matrix. So what this lemma does is it distinguishes three cases: no defective, exactly one defective, and two or more defectives. So when there's exactly one defective, it returns which item it is, and when there's no defective, it returns no items. All tests are fixed in advance, so it's fully non-adaptive. We can run all the tests in parallel without any relation in between them. Why this lemma matters? Because the cost of this lemma is essentially log of n. So in information, theoretically, near optimal for naming one of the n items. Okay, so where are we going to use this lemma? Lemma number 9. It is the inner subroutine of the non-adaptive randomized upper bound, theorem 11, which we're going to see in the next slide. If we subsample with probability of 1 divided by 2, um, and we're going to use lemma number 9 to detect that this sample has exactly one detective. So we're going to be sampling data and sampling the tests. And based on this, we're gonna exactly detect one defective item using lemma number 9 with the cost of a log of n. So theorem number 11, it's the non-adaptive randomized upper bound where D is known. So the theorem says like this: there is a non-adaptive randomized algorithm that makes O of L log n divided by D tests, and with probability of greater than 1 minus delta detects L defective items. So the algorithm goes like this. If we run T, which is the number of iterations or tests, with that is corresponds to the test complexity of L plus log 1 divided by delta parallel iterations. And in each iteration, we choose an element from X to the group of X prime with probability of 1 divided by 2D. So all the elements in the group X, which is the all the items that we're trying to find the defectives on. And we put each item in X into X prime with a probability of 1 divided by 2D. And we say that if the size of X prime is smaller than 4n divided by D, we use lemma 9 to check if the group X prime has exactly one defective item, and if so, we find it. Otherwise, we skip this iteration. Okay, so we run T iterations, which is the number of tests, and in each iteration, we create an X prime group, a set of X prime, which is which is a subset of the whole group X items with a probability for each item. So every iteration we get a new X prime set. And for this X prime, if it's smaller than 4n divided by D, we use lemma 9 to check if it has exactly one defective item. Okay, if so, we find it. So why it works, the probability of X prime has exactly one defective is this probability if we calculate it by regular math. So the probability of A is the event that it has, that X prime, the group X prime that we created, or the set that X prime that we created has only one defective item. So it equals to D choose 1 times 1 divided by D, which is the probability, times the counter probability, okay? Multiplied by 1. And this, if we bound this, if we lower bound this, we get that it's greater or equal to 1 divided by 10. And by Chernoff, if we want to calculate the probability or estimate the probability of the size of X prime to be greater than 4n divided by D, we can say that it's smaller or equal to, by Chernoff, if we plug Chernoff here, we say that it's smaller or equal than this operand here, and we can also put an upper bound on it, which is 1 divided by 20. So by Chernoff, the probability of the size of X prime to be greater than 4n divided by D is smaller than 1 divided by 20. So now we can see that at each iteration, we find a new defective item with probability greater than 7 divided 160. And after O of L plus L log 1 divided by delta iterations, L defective items are found with probability of 1 minus delta, greater than 1 minus delta. So at each iteration, we have a probability to find a defective items, which is 7 divided by 160. And if we run over L plus log 1 divided by delta iterations, we get that we find L defective items within this algorithm. with probability greater or equal to 1 minus delta. So we're using lemma 9, which plugs in the log n divided by d test complexity, and we are running L tests on this to get the results. So in total, it's O of number of tests, L times the complexity of each test, which is used by lemma number 9, which is the log n divided by d. Um, this is the upper bound, and for result number 14, we can use theorem number 5 to get the lower bound, which is identical to the proof of theorem number 5 that we have talked about. So here are the results of 13 and 14. Moving on to the next one. So theorem 13, which is result number 15, there's a non-adaptive randomized algorithm that makes OL of log squared of n tests with probability greater or equal to 1 minus delta, detects L defectives when D is unknown. So we have the setting of D is unknown, and we can detect L defective items with a probability greater than 1 minus delta. And this test has to take L log squared of n for the upper bound where D is unknown. So, okay, the algorithm here is fairly simple. So in parallel, we run a non-adaptive estimator for D, which is lemma number 5. We want to estimate the number of defective items, which is D, to make this known, to ease on this problem and make it a known problem, and then maybe use theorem 11. So we run in parallel a non-adaptive estimator for D, which gives us that the big D lies in between D divided by 2 and 2D using O of log 1 divided by delta times log of n tests. So to get D, we need log of 1 divided by delta times log n tests. So also in parallel, for each guess of D, we denote that D equals 2 to the powers of I times L, and I is the number in between 1 and log n divided by L. Okay, so we run the algorithm of theorem 11, assuming that D is approximately big D. Okay, so we assume that the D that we have found is approximately to the actual unknown number of defective items in the group. And the total tests per guess are of O of L log n divided by D. So this is the total number of tests, and each test requires a log n tests. Okay, so the sum over all the guesses. So we're iterating over each guess. We're guessing D and then running theorem 11, which where D we're finding the upper bound where D is known. So if we sum this over all of the iterations of I, which is I equals 1 to L log n divided by delta, we get the following: L times log of n divided by 2 to the powers of I times L, which is equal to, by simple math, equal to L times log squared n. And we know that the correct guess D, which is approximately close to the actual defective items, will succeed. The estimator tells us which output to trust. Okay, so the estimator that we have created will tell us approximately which result to trust, and this gives us the upper bound. One thing to note is that this is worse than the D known case by a factor of log n. So the upper bound for a randomized non-adaptive algorithm is worse by log n factor just by the fact that D is unknown. Okay, just by the fact that we don't know D, this makes the algorithm a little bit makes the upper bound cost more in terms of runtime or test complexity. Moving on to theorem number 14, the non-adaptive randomized lower bound where D is unknown. So if we let C be smaller than 1, any constant, where L is smaller or equal to n to the power of C, and let D be unknown to the algorithm. So we don't know the number of total defective items. Any non-adaptive randomized algorithm that with probability at least 3/4 detects L defective items must make at least gamma of L log squared n divided by log L plus log n tests. So the difference here from the previous one where um, it was an upper bound is that we didn't have this factor on the bottom. We had only the denominator, okay? So which is the upper bound. Um, so where it sits, so the upper bound, as we said from the last theorem, is L log squared of n, and the gap between them is this factor. So the lower bound is smaller by this factor. Um, One thing is that why D is unknown makes it hard is all tests are fixed in advance and must work for every possible value of D at once. So if the tests are fixed, we must um, work for every possible value of D, but D is unknown, so we can't use the fixed tests, and the algorithm cannot tune the size of its tests to D. It must hedge across all scales. And the proof is in one line, test gets spread thin across many size scales. Okay, so we take all the tests and we spread them into many size scales. And by Markov, we can find a starved scale where the adversary hides D exactly here. And hence, from this, we can get that too few useful tests remain. And from this, we can use theorem 12 to get the probability. Um, So now we have the theorem 14, why D is unknown makes it hard. Okay, so let's go over the short proof of it. So the proof technique will explain the word. So partition the range of possible tests sizes into sizes of Q into R equals log n divided by log R intervals, Ni, which we take all the tests and we divide them into intervals. Um, and the test sizes of these intervals is the sizes of Q. Okay, so we plug R to equal L times log n, and we get that by Markov's inequality there exists an interval Nj where the algorithm makes at most L divided by C times log n tests. And from here, we can choose that we can choose D to be L log n to the powers of 8j plus 4. And then tests with size Q too small all give answer 0. Miss all defectives. There are no defectives in groups that are very small. Tests with Q too large all give answer 1. Always hit a defective. So if the test group is very big, we definitely get at least one defective. Um, and only test in NJ, which is um, these intervals where the size of J is equal to this, um, we get an actual information where whether there are defectives or no defectives. And we know that there are too few tests in NJ to find L defectives. So by the lower bound from theorem 12, we get that for each NJ, we only guarantee to find one defective. So we need to run at least L tests like these. And from there, we get this factor of L log n squared times L divided by log L plus log of n. One thing to notice is that there is a gap of this factor between this theorem where the lower bound of D unknown and the upper bound of D unknown on the non-adaptive randomized, and this is still an open problem which hasn't been solved yet. If this factor could be even proven to be minimized to give us the same lower and upper bound between them, which is L log squared of n. So let's go over the summary and compare the results. This is the table of detecting L defective items out of out of D defective items. So let's take a look first of all on the adaptive results. We can see that on the adaptive randomized, the upper and lower bound are the same, which is L log n divided by D. And if we look at the upper bound between deterministic and randomized, which is a result 1 and 5, we can see that there is a factor of L divided by D on the log n in the test complexity. On the deterministic, since we know everything that we have, we know the number the algorithm is deterministic, so it has a specific flow that it goes through, and the randomized, then we pay a factor of d divided by L, um, more tests to prove the upper bound. One more thing is that also in the adaptive, where d is unknown randomized, we get the same result, where actually we get for the adaptive randomized d is known or unknown, we have the same results for all of them. So it doesn't really matter whether d is known or not known. Um, So we can see also that in that the randomized algorithm gain a factor of d divided by L over deterministic in most settings. We can see it's exactly what we talked about at the moment, the difference between 1 and 5, and also 3, 7, and 4 and 8. Uh, Another point is that knowing D helps most in the non-adaptive randomized case. So the non-adaptive randomized. And we also can see that the adaptive randomized achieves the best bounds, which is L log n divided by D, which is the lowest bounds ever, lowest test bounds for here. So if we're trying to detect L defective items out of D defective items, it's mostly recommended to use the adaptive randomized, where D, the number of defectives, is known, or also where D is unknown. So this will give us the least number of the least test complexity with lower and upper bound. So key takeaways from this paper is finding L out of D defective is strictly easier than finding all D in most settings, savings of factor D divided by L, which is the table we've seen earlier. Exception is the non-adaptive deterministics, even when L equals 1, costs D log n divided by D. This is the paper's most surprising result, actually. Non-adaptive deterministic. We have the non-adaptive deterministic. So even if L equals to 1, we still pay the same complexity, the same upper and lower bound complexity of when we want to detect D defective items out of N, without using. So it's like the original upper and lower bound that other papers have found of detecting D defective items. So it doesn't matter if L is 1 or 2, using these algorithms, we have to pay the same as finding D defective items. So bullet point number 3 is randomization is most powerful in the non-adaptive setting. It enables the D divided by L savings that determinism cannot achieve. We have seen this before. Knowing D helps significantly only in the non-adaptive randomized factor log n gap between the known and the unknown. Let's take a look at this. Knowing D helps significantly only in the non-adaptive randomized. So non-adaptive and randomized. We can see here. So where D is unknown or D is known, you can see that there is a log squared factor. And another open result, which we have seen in theorem 14, that the difference between the upper bound and lower bound is the factor log n plus log of n, which is still an open matter to close in this subject and in this paper. And I think that's mostly it. So I want to say thank you for this opportunity to read and understand this paper. It was actually a tough paper to understand. There was a lot of mathematical equations and proofs. Really enjoyed this process, and that's about it. Thank you very much, and good luck.